Okay, hi everyone. Let's continue. So let me start with a little recap of what we have been doing, and slowly proceed from there. And so first, we discussed that we're studying the two amplitude, and we studied first the unitarity property. Last time we talked about analyticity, and so remember the lecture one. The idea was that we will come up with some basic principles, and then we will try to use them. And so the last principle, which is missing here, and which let's discuss now a bit, it's a principle of crossing. I also realized maybe I would like to make a comment about analyticity in our discussion last time, is that we were drawing these graphs which look like Feynman graphs, and then I connected to Feynman graphs. And this is applicable to any theory. In particular, it's applicable to QCD, but this kind of graphs, do not confuse, there are no quarks and gluons in the graphs I'm drawing. All the states are asymptotic states. So this box, if I want to read off the Landau curve from it, then you have to put pions or whatever asymptotic states are in this diagram. Just not confuse the two. And so here we discuss briefly normal thresholds and Landau curves, and we will continue doing so. And I also want to discuss more Landau curves today. It's a very interesting story. Okay, so let's discuss crossing. And remember, we already, if I look at, say, let me fix T to be something, say, physical, well, T, let's say T negative. Then we already figured that based on unitarity, we have a cut in the S-plane, which starts at, say, 4m squared. And, well, there are other cuts here, which start, say, can be at 9m squared. Let me put them all here along the real axis, so they all go here. Moreover, the physical amplitude was defined as approach, say, from above. This was I epsilon prescription. So if you will to measure something in the actual experiment, we approach it from above. And here I try to motivate that if you approach this guy from below, the same cut, you have T star S of T. This is a complex conjugate amplitude, and therefore, when you take a discontinuity, it's the same as you take in T minus T star. This is what enters the unitarity equation. So now, let's ask what happens in this plane a little bit far away from this unitarity cut. And what happens is that, well, say, in the upper half plane and lower half plane, it is analytic, and this is related to causality. But then, as you take S to be negative, you will find another cut. In fact, you'll find, again, infinitely many cuts, which are related to the fact that that the same amplitude describes processes not only in S channel, which was, remember, as S larger than 4m squared, say T negative, but also, let's say there is a U channel, where U is defined as 4n squared minus s minus t, and when this thing becomes larger than 4n squared, and t can also be negative, say, this is a physical U channel, and S channel describes scattering in the particle 1, 2 going to 3, 4, and U channel defines 1, 4 going to 3. So a priori, the statement is that, okay, you can have an analytic continuation of this function, and it has nothing to do with the U channel, but what happens is that, in fact, if you take this function, and let's say we take U equal 4n squared, the branch point U equal 4n squared, we plug the definition, so it's minus s minus t equal to 0, so it's s equals to minus t. You have a cut, and the same function, the same analytic function, same analytic function t of st describes scattering in the crossed channel. And in the crossed channel means here the operation of crossing, you take a pair of particles, one in the initial state, you move it to the outer state, outgoing state, and you take one in the out state, you go into initial state. So the statement is, in fact, that if you take this function and you continue here, and know that why here, because if you again go to the U channel, the I epsilon prescription is that you should have t of in the U channel some function where we take U from above, so U from plus I epsilon, like we took S plus I epsilon 0, then if you translate to U plus I epsilon, it will be S from minus I epsilon. So in other words, if this process describes for you the process 1, 2, 3, 4, then by analytic continuation, you get here T 1, 4, 2, 3. And for simplicity, so now let me take all the particles to be neutral and identical. So this fact that you have the same function describing processes in all channels is called crossing. And if you go here equivalently, then you have T star 1, 4, 2, 3, like you have T star of 1, 2, 3, 4 here. Now, in other words, let me write just a formula. If I have all particles to be identical neutral scalars, you can write the following equation, something like this: Ts T ut, so it is fully permutation invariant. Well, the real meaning of this is that if you want the actual meaning of crossing symmetry, usually it's a statement that there is a single analytic function that describes scattering in cross channels. But effectively, if now you have this analytic function and say if all the particles are identical, all channels are the same, 1, 4, 2, 3 are the same particles, so it's in fact the same function. So in all three channels, you describe the same function, and there is a region of analyticity which connects them. Now, what I told you is the simplest possible version of it, and what could have failed? So, yeah, first of all, if you have particles which are different from antiparticles, when the operations of crossing, when you analytically continue here, the particles are changed to antiparticles. This is one comment, but let me ignore that. Second, you could have asked the following question. How do I know that there is this region here? How do I know there is this region here where I can go through? That there is no some crazy singularity that lives here. And in fact, during the last lecture, we saw that sometimes we have this sort of singularities, which are anomalous thresholds, which started before 4m squared. So there might be some, say, cut, which maybe go from here, and it completely closes the path. So it might happen, and in fact, if you external, and here the statement is that, I said it again, but let me repeat it, is that if we consider the scattering of lightest particles, we believe that such things do not happen. There are various arguments that there are no anomalous thresholds. However, if you consider theory of particles which are not the lightest particles, you might run into this trouble. And to connect to the previous lecture, remember, when we consider this diagram, the anomalous threshold, and this particle was m, and this was some m, the anomalous threshold only appeared when m squared was larger or equal than 2m squared. So this is precisely the condition that the external particle is not the lightest particle, because the lightest particle is m, and if the external particle is m, then there is no anomalous threshold. So this is a general thing to keep in mind. So in case if you do not have this path, you can still establish crossing symmetry. However, the path from the, say, S channel to the U channel is more complicated, and this is what is known as as Bros-Epstein-Glaser path. And the idea is just this. You first continue along this upper arch. You say keep T fixed and you continue S like that. And then you keep S fixed and you continue in T. And then you will find that you will land up on, in fact, not on T star, but on the amplitude you want. And so on the, if you draw the, remember our Mandelstam plane, S, T, U, 0, 4n squared, 0, 4n squared, 0, 4n squared. So then you can start in the physical region in the S channel and go to, say, U channel like this. This is literally, well, carefully, if you do this, you should. What I mean by this, I first say here, I keep, say, U fixed and I continue in the upper half plane of S, and then I keep S fixed and I continue like this. So, and the idea is that if you have Bros-Epstein-Glaser path, it's a path that avoids going through this question mark region. Okay, but this is just some technical subtlety. I want you maybe just so that you heard these words. This is something which is common. The punchline, and for me, I will focus on the scattering of lightest particles. And so for me, the picture would be that there is nothing happening in there, and in between these two cuts, S channel cut and the U channel cut. And so you can go through.
Sorry, Sasha.
Yep.
The fact that this path does not cross any other singularity is known, or?
Yeah, so the idea is that there is an axiomatic domain of analyticity, which roughly this, you cut out some potato around the question mark, and then this path avoids all these potatoes. So, okay, so the punchline is, at this point, is the following, that, and I want you to really, maybe let me just draw this picture, because this is one of the most frequently drawn picture in the subject. This is just this, that in the simplest case, the amplitude TST, say for fixed T negative, is has the following analytic property. We have two cuts, and everything else is here is analytic. And in fact, this so of course, since some branch cuts, this function lives on some Riemann surface, and this Riemann sheet, which is connected to the physical region, by which I mean that if you go here, this is the physical amplitude, and then you go everywhere without crossing any normal threshold. This is called physical sheet. So at this point, we have the following problem. We have this function, which say has these cuts. It is crossing symmetric. It is it has some analyticity properties, and on these cuts, the discontinuity satisfies unitarity. We also discussed that it was, remember, at infinity polynomially bounded. So this is the minimal picture that of a non-perturbative scattering amplitude that we have in mind. This is a basic principles. Let me now go back, sorry, one step, and discuss going beyond this picture. So here you might have noticed that, say, if I have T fixed, the analytic structure is given by this complex plane without unitarity cuts. These are called unitarity cuts. U channel. And this is the S channel unitarity cut. But of course, this is a function of two variables, and it's natural to make both of them complex. And so the question is, what happens? What happens then? And again, to connect, because I didn't really have time to discuss last time the solutions and Landau equations, I want to go back step by step and discuss in some detail the box diagram. So the box diagram is just this. This Feynman graph, I take for simplicity all the particles to have the same mass. 17. Yeah, sorry. One comment which I have to say. How do you can ask, how do you establish this this picture? This is not a trivial task. It's something which is kind of clearly true and holds in perturbation theory. Non-perturbatively, it's some work, and this is a famous result by Ross, Epstein, and Glaser, who managed to prove this for, say, 4 particles. So for 2-to-2 scattering, this has been proven within quantum field theory. If we go to something like gravity, again, we don't know if it's correct, but one thing in the subject is that there is some compelling picture. It's consistent with everything we know, and so we believe that all these general principles which I'm telling you about, they also hold in gravity, even though this hasn't been proven.
You know this proof for 5? Because is it what's the principle behind? Is it LSZ, and so it's crossing of the correlation function, or is something else?
Yeah. So I posted on Slack. You're probably not there. Yeah. So there is a So, yeah, the argument starts with LSZ, and there is this paper by Sebastian Mizera and say Appendix A in his paper, where he just very condensely reviews the argument. And it's a very subtle argument because you start with LSZ, you write some commutator. So this commutator, because of causality, vanishes in some region. There is some spectrality condition. You start with some off-shell Green's function. You have to go through analytic completion. So it's a bit of elaborate argument, yeah. But so effectively, you use everything. We use causality, spectrality, LSZ, analytic completion, and then it works. For 4 particles, there is some work by Bros for 2 to 3, but beyond 2 to 3, non-perturbatively, it hasn't been done. So I guess this year, Sebastian had this paper for planar diagrams, finite graphs. So this is not something very simple. In fact, it is kind of a miracle that we started with just a function of energy and angle, and then we discover this beautiful complex function which lives in the complex plane, and it connects experiment in one channel to experiment in the other channel, and so it's a very neat structure. So let me start with this graph, and in fact, let me write it some schematically, some integral over loop momentum, and then we can introduce Feynman parameters. Number of propagators here will be 4. Here, the right side of P, whereas, again, for here will be 4, but okay, right, it doesn't matter. But this, I just want to say that this formula is general. What I will write now has not really much to do with the box. And the function psi by construction is a sum of over propagators, Feynman parameter, and propagator particle that propagates here. If all masses are equal, you just set m to 0. Now, I talked last time that, yeah, this integral is 0 and 1. That if we are interested in analytic structure of this integral, we want to understand when it develops some kind of branch cut or singularity. So the way you think about this integral together with I epsilon prescription, say the loop momentum, it's some integral in a complex space, say in some plane. It can be K plane, it can be alpha plane. So all these variables, we can think of them being complex, and this integral defines a contour in this space. Now, this function psi, being a sum of these propagators, naturally can become 0. So it can develop as 0. So, however, because it's an integral, it's analytic, just having a 0 crossing the integration contour is not enough because you can deform it. So really, to develop a non-analyticity, you want to have a pinch. It's a situation where the contour is pinched between the two poles of the function psi. So the condition for the pinch is then what is the Landau singularities, and in this basis, you see, we want to have to develop a singularity. We want to have a pinch in every variable, and so the first form of the Landau equations is just this. And so for each variable, we want to have a pinch. Now, again, there is several subtleties. These vertices can have numerators. there could be some cancellation. So Landau equations are necessary conditions for developing in singularities. They could not be sufficient, but in generically we expect that unless some cancellation happens, then they're there. And so here you see all the things we discussed last time appear, which is that if you differentiate psi over d alpha, the particle is on shell. This is just an on-shell condition. So particles are on shell. Well, the momentum in every vertex is conserved by just construction of Feynman graph. And this condition gives us, remember that the conditions of the sum over the loop of alpha times k is equal to 0. And last time you can think of this as an interpretation of having a movie. So if you go over, if it's a process in space-time, if you start at some point and you go over it, you should come back with some points, and this alpha i's for this process in space-time, you can think of them as proper time. So the interval of going from this point to this point is alpha I, say ki. This is a delta xi. And then this condition is just so that as you go around the loop, the intervals delta xi is equal to 0. But here you see how it emerged. And finally, you see that if we start with this graph, all the alphas are naturally positive. This was another condition which I didn't really motivate last time. So this is one form of the Landau equation. There is another form which just because you can the integral over loop moment is Gaussian, so you can integrate it over it. And if you integrate over it, you get the following formula. Well, you get this integral is equal to the integral over d alpha I. You have this still this delta function. You have something in the numerator, some power, let me ignore it. And you have some function d in the denominator, and you can compute this function d by just doing Gaussian integral. You can put sine to the exponent, integrate over k. But the important point is that, and there is a graph theoretical way to write down d. It's related to some trees of the graphs. So you look at the graph, you can write down d directly or do this integral, doesn't matter. But what is important is that d is a homogeneous function of alpha. So d is proportional to alpha I d alpha I d. And so again, the Landau equations in this form, you want to have a pinch in each variable. And so the Landau equations just become d over d alpha I equal to 0. So let me do the example, which is a box diagram, finally. And it is given by, we have 4 propagators. So it goes from 1 to 4. Delta minus sum over alpha I. And we have here S 1 alpha 3 plus T alpha 2 alpha 4 plus M squared. Here I can write alpha 1 alpha 2 plus alpha 2 alpha 3 plus alpha 1 alpha 4 plus alpha 3 alpha 4 minus 1, and this guy squared. So this one, I told you the function is homogeneous. Here it is because you can exchange 1 to sum of alpha square, so this polynomial is quadratic enough. Now you might say, okay, well, I was a bit fast, you know, there could be a pinch, but what if a pole approaches the endpoint? You're right. This is another mechanism for singularity, but it's kind of boring, but it is there. Nevertheless, so this is the answer for this diagram. Now let's just write these equations, and let me say d alpha over d alpha 1.
Sorry, Sasha.
Yeah.
Let me understand if I understood.
Yeah.
So these are the conditions for singularities potentially to appear. The first conditions are this psi, delta psi of delta alpha and delta psi of delta k equal to 0.
Yeah.
And then there is another condition.
No. So that's it.
That's it. Okay.
Now, what I just did, I took this integral and I did the k integral.
Yeah.
And so I'm writing in new form. I get rid of the k integral, so I just have d now.
It's in
so
there.
I only have pinch in alpha I. So k is gone.
Okay, so these are either you have it in that form there, conditions, or
these are equivalent things.
Okay,
Yeah.
Thank you. Very good.
So sometimes you might see it this way. So I did it because I will now want to do it this way for the box. And if I want to connect to this classical processes in space-time, then it's this form. That's the idea. So if you do this differentiation of this function, you will find s minus 4m squared alpha 3 minus 2m squared alpha 4 equal to 0. And I think for the d alpha 2, it is like this. And also because of crossing symmetry or with some hindsight, I know that on the solution to the Landau equation, you can go over all four, but in fact, on the solution, you can have this. This is just because of the symmetry. The graph has two Z2 symmetries, either horizontal or vertical flip, and the solutions of Landau equations, they inherit these symmetries. So, okay, you can just either differentiate with all four, and then you'll find the same thing, or I differentiate with respect to two, and I put these two things. And you see what those conditions, you see what you get is a homogeneous system of equations, so for alpha 3 and alpha 4, and well, it can only have a solution, a trivial solution, its determinant is 0. So this is general situation for any Feynman graph. If you write like this, you get a homogeneous system of equations, and then for it to have a trivial solution, you want a determinant of this matrix. So let me write it as m alpha equal to 0, and the Landau equations lead to the locus determinant of m equals to s minus 4m squared t minus 4m squared minus 4m equal to 0. Equal to 0. So this is the equation for the Landau curve of this graph. Okay, now let me discuss what's the significance of that, and connect also to this discussion which I want to have about analyticity in both variables. So I showed you some picture, but I want to discuss also analyticity in both variables. And so here at this point, well, I can leave you with this integral, or I can tell you what is the result of doing this integral. And let me do that. Just write the answer. answer is this. We already wrote it last time, so I'll just write it again. And this representation is known as a Mandelstam representation. I already said it last time. And rho S prime T prime has a support when you are above the Landau curve. So the branch point is the Landau curve. You have S prime minus 4m squared T prime minus 4m squared minus 4m to the 4 positive. So this is a theta function. It's 1 when this is satisfied and 0 otherwise. And here you have S prime T prime 1/2. And we have a square root okay. Very, very good. So, what is the analytic structure of this function? Now, let's just analyze this example because it's already interesting enough and you can learn things from it. Well, first of all, I told you that when, say, t is negative, we expect to have a brick. So let's just reproduce this picture that I showed you. So there is this cut. This diagram does not have a U-channel cut because it does not describe a scattering in the U-channel, but it does have an S-channel cut because we can take So we expect that this function, this integral, has a T-channel cut. Sorry, S-channel cut and T-channel cut. Yes, and also I told you before that in perturbation theory you find the diagrams, the result to be crossing symmetric, and here it's again obvious. This function is invariant under exchange of S and T, and you can go from the physical channel of S the physical channel of T just going in a complex plane. So it is a crossing symmetric function. And to understand this cut, let me draw a little bit how does this locus looks. How does this look? This curve. What is this space? Well, space is this. So let me put here say S prime. T prime. You see that if you want to satisfy this condition that this thing is positive, and let's say S prime goes to 4n squared from above, then you see that for it to be satisfied, T prime has to go to infinity because it's multiplied by smaller and smaller. So you see the curve starts like here. Similarly in the same channel, so in fact, you have like this is the Landau curve and the double spectral density has a support here. This is just this theta function, this equation. Now, let's say we want to understand the analytic structure in S. Well, you see that as you approach 4n squared, rho has a support. If I take, say, discontinuity in S from this formula, it's just, I guess we're all familiar with this formula, S prime minus S plus I epsilon minus S prime minus S minus I epsilon is equal to minus 2 pi I delta S prime minus S. So taking the discontinuity is simply setting this to delta function. And so you see, if you go above S, above 4n squared, because you have a support. So this point here is 4n squared, 4n squared. So you will have a support by this somehow by this integral. and therefore the cut is reproduced. So just the fact that the double spectral density approaches a normal threshold immediately through this formula gives you the fact that in the S-plane you will have a cut. Just because if you put a delta function here, you will have a non-trivial contribution. So, in fact, this property of Landau curves that they are asymptotic to normal thresholds, normal threshold being t equal 4m squared or s equal 4m squared, is completely general. Now you see that what is the analytic property? What are the properties of this guy? So there is one property which is very cool and very non-obvious, or quite non-obvious. At least I don't know how to see it just by staring at this formula. But it is a true fact, and it is derived in the notes. And the fact is the following. Let me go to the region where both S and T are larger than 4m squared. Now, if I go to this region, I can choose different path. I can take both S and T and go like this, say both from above, or take both from below, or one from above and one from below. Right? This is a function which I start and I can analytically continue. Now, if you look at this integral, okay, what it corresponds to, you will add some I epsilon here or here, and you can ask, is there any difference between the two? And in fact, there is. If you go from the direction I plus minus, before going that, let me also say that something which is manifest in this formula is that, in fact, it's not just analytic in the S-plane for T negative. It's really analytic in the product of C2, C for S, minus unitarity cut, times C of T minus unitarity cut. This is just what this formula says. There are no other singularities. It's just when S prime and T prime goes to start from 4. So if you stay away from these two cuts, no matter what S and T are, the function is analytic. So in fact, what I showed you before, there was unitarity in one cut in one plane for fixed T, but for the Feynman graph, you see that you get a singularity in product of two planes with just unitarity cuts. Now, of course, the question is, well, we will come back if it's always the case, but now let me go back here. So if you go and you consider this integral from this approach, you will find that it is regular along this locus. So in fact, you see that it seems like there is a singularity here, which is a square root singularity. But if you approach it like this, you'll find that it's regular. And if you approach it like this, you'll find that it's singular. Well, and the same for minus minus and minus plus. Now, why is it the case? So this is related to the following things. That in fact, now that we think of S and T being complex, the Landau curve is a complex surface. It's a C1 surface and C2. So you can ask, where does it go? Like in which direction, as we make S and T complex, where does the surface go? Well, and you see that, let's say we start on the complex surface and we make S a little bit imaginary. So we'll have imaginary S times T minus 4m squared plus imaginary T times S minus 4m squared. I'm just taking the imaginary part of this equation. And you see that since S and T are both here on the Landau surface are positive, the imaginary part of T and imaginary part of S has to be the opposite sign. So the Landau surface, if we think of this as a complex surface, in fact continues starting from this curve. If I could draw in 4 dimensions, I could depict it, but since we can only have 2, at most 3, then I'll just tell you based on this equations that you see that as a complex surface, Landau surface continues in the direction in this equation. And if this surface would have been singular as a complex surface, then this picture would not be correct. You would see some complex singularities that as goes becomes complex, t becomes negative. So it's better be regular, and this is indeed the case. You'll find that it's irregular. There is nothing on this complex surface. Nothing happens. Nevertheless, you have this I++, which is singular, and it's consistent with the fact that Landau equations control non-analyticity. So what is the lesson from all that? Well, first of all, you see that, and that's what people observed in the past, you very quickly run into this question of analyzing complex surfaces and these equations. So here we just have a simple equation, but the more complicated Feynman graph you go, the more complicated they become. And so then the question becomes, okay, how does a given complex surface, first of all, what is it? And then is it singular or not? And how, if it is non-singular, can it become singular or non-singular? And this becomes very, very complicated very quickly. This theory of these surfaces and how they intersect and how the singularities emerge. And so people just very quickly sort of lost their way there, because already if you take this graph, this was the end of the story. If you take this graph, they found a complex singularity which was very complicated, and this graph has the name Eck-node, because Eck-node is a type of singularity which you get from here. So very quickly people find some complications, and however, that's one thing that people found. But second thing, people found that if you consider scattering of lightest particles, so let's say you have a theory with various stable particles, and take the lightest particle and you make it external, this doesn't seem to happen. This seemingly does not happen, and this being here some spooky singularities, spooky complex singularities.
So basically these S and T singularities or something you could have guessed before, right? This was sure that they would be there. But now you say that there was a hunt for other type of singularities.
Yeah.
And this Eck-node already shows something.
Yeah. You get a singularity which is a complex singularity, which means and let me okay. You asked me this question, I will use it as a chance to make another comment which I wanted to make. So okay, that's I just wanted to show you some complexities that you get already here. So let's say you ask, we go back to the triangle example. This M, and surely it has a normal threshold cut for M squared, and then we found that depending on M, it has also an anomalous threshold. Yeah. So you could ask, well, how does this anomalous threshold appears? Let me start with this M being equal to M, and then increase it as M squared larger than 2M squared, right? So I told you that when this large M squared is larger than 2 little m squared, there is an anomalous threshold, and when it's less, there is none. So what happens? Well, what happens is that let's start with capital M being small m. If you look at this threshold, there is just this cut, normal threshold on the physical sheet and nothing else. As you increase m, there is some crazy cut creeping out from the second sheet and entering the physical sheet. So this what happens as m increase. And the same story happens with these singularities, which is that, well, let's say you start with t negative, and this nice picture, that I showed you, we all draw. When t is negative, we just have unitarity cuts. Let's say you start increasing t. How do you know that no crazy stuff is coming out from the physical sheet? Yes.
Sorry, for the triangle diagram, what is the support of rho then?
There is no rho. So here I'm talking just about one discontinuity, and instead of t, I'm using capital M.
But couldn't you write a mathematical representation for that?
Very good. So indeed we can take this box and we can play the same game where I just take two legs and then there is a contraction and there is a triangle effectively.
Yeah.
So yes, you can play the same game, and in fact again Mandelstam did it. So you can start taking this box, which I took with all equal mass, and start increasing this mass. So what happens is that this guy starts changing its shape. And so what happens, it's really crazy what happens, in fact. So you start getting something like, it goes like this, and like this.
I see, so it's still asymptotes to the normal threshold,
It
but it
asymptotes
goes
to
down.
normal threshold, and this is a normal threshold. This is a normal threshold. And in fact, what happens is that here I told you I++ is singular. I think as you cross the point, here I plus minus become singular. There is some funny business, and so you can try to understand that again as always complex surfaces and how they link. But yeah, so what happens is that this guy bends. And at first you still have this Mandelstam representation, but with a different support, and then at some point you just lose it. You're losing Mandelstam representation. So the idea why let me just now, I'm trying to summarize this many years of developments. So there are complex singularities for general graphs, but second, if you say scattering of lightest particles, there seem to be none. And in fact, this has a name, which is this is a conjecture, but people use it widely these days, or some people use it at least. And the reason people use it, okay, either you say, fine, I'm either working with this axiomatic domain of analyticity, or it's all hopeless, I'm just not doing anything, or here there is some reasonable conjecture, for which we don't have concrete examples, and it's called the lightest particle maximal analyticity. It's a statement that if you consider scattering of lightest particles, then this T of S and T on the physical sheet is analytic in the product of C minus unitarity cuts for S times C of T. So effectively, it's the same as what you get from the Mandelstam representation. So this is an interesting conjecture. It hasn't been proven, but it hasn't been disproven. And its tricky part comes exactly from that as you start, say, for physical T, and you have some domain of analyticity which you established, say, which was this. Again, let me draw this picture. For T negative, this is something that you can establish using some axioms of quantum field theory. But as we start continuing T to be positive, how do you know that some crazy stuff is not popping out from the second sheet? And this is, okay, this is an open problem, but historically that's a punchline. If you consider a Feynman graphs where particles heavier particles involved, you get complex singularities. You consider lightest particles, that's the only singularities we have. So for the, let's say, pions, we believe this is correct. Impurity 3. Okay, so that's a set of comments which I wanted to make. And now it's perfectly 1 hour, so let me pause and chair, please tell us when we reconvene.
10 minutes?
Yeah.
10 minutes. Yeah, if you have questions, just speak aloud, if you're allowed to. We can hear you from here.
Or we can discuss tonight.
Or we can discuss tonight and just have a 10-minute break.
Yeah, so what we did is that in the paper is just that. So if you have all the graphs where at least in one channel you just have two particles,
okay,
then you can write down explicitly the equations for Landau curve. It's very easy.
It always reduces.
Because it's related to the two-particle unitarity, you know, it's im t, im, imaginary part is equal to t square.
I see. So you mean whatever happens.
Yeah. Whenever you can find such a cut, it's kind of a solved problem.
I see.
But it's related to elastic unitarity, and we wanted to understand what about multi-particle unitarity. And so for multi-particle unitarity, it means you need to find all the graphs which have at least more than two particles in each channel.
So I understand. But then a diagram of this kind.
Yeah.
You're saying if there is anything that is like this, and then whatever you have, this is.
Oh no. Well, when I talk about Landau graph, it's maximal. So all the propagators are cut. So okay, if you just cut this two, you don't care about the block.
You don't care about the block because the kinematics is fixed by this.
Yeah.
So which diagram you were saying that always has the two?
Yes. For example, you can have something like this. You know.
Okay.
You know.
See where there is not. You mean this kind of thing where we have two? Well, but still.
You just have. Whenever, so let's say you talk about maximal cuts. So we put all the propagators. So then you see in this channel, it's just elastic scattering.
Yeah.
So this is boring. This will be controlled by elastic unitarity.
The unitarity, exactly. We fixed that this is.
Yes. You can either solve Landau equations or you can just directly find Landau curves by some other tricks.
But this is one non-analyticity. But how do you know there are no others?
Well, the idea is that's a minimal. There is a minimal set which is required by unitarity. Then you can postulate some crazy new one, but this is not required by unitarity. So I'm saying the minimal set.
Because this is the here you're saying in the article you're just proving what non-analyticity needs to be there.
Well, this is a kind of this already we assume it's a solved problem because we have explicit equations for all these Landau curves. Super easy. But the non-trivial question is what happens if you have multi-particle on both channels? Yeah. Which means you have say 4 and 4. That's the first thing that happens.
In here.
In both channels, in S and T. Because if you find at least one channel, you know, if you draw something like this. Then you go to like 4, but just start here and you're fine.
So you need multiple,
Exactly. And so what we did is just a graph theoretically, try to find all the graphs which have 4 particle cuts and which have the solutions to Landau equation. And the claim is that this is you have this infinite chains of triangles. And the relief accumulations of Landau curves.
Okay, we look immediately. Thank you very much. But
practically, I don't know if it's
But then in this biggest quest, once they found this anecdote or
Acno,
was this kind of the end of this program because there was something which was
I can tell you what happens is that this was the end of the problem for the following reason. So even we solved this problem for this alpha positive Landau equations when alpha between 0 and 1.
Okay.
But what happens, imagine you start with this is a deformed contour for, say, for the physical kinematics for Feynman graph.
Okay.
Now, let's say you want to go to...
Is that part in alpha?
Alpha, yeah. Let's say you want to go to unphysical region, which is T positive and S positive. As you do it, imagine there is some pole comes and start dragging your contour. So you just deform, deform, deform. So you arrive somewhere where your contour is like that.
Yeah.
And then there is a pinch in the complex plane.
Okay, no longer.
So then this is a pinch for complex alpha. And if you write Landau equations, you get gazillions of solutions for complex alpha and only very few for positive and real. But if you have a solution, you have to establish by dragging it back if it's there or not. And this global question of dragging contours is just so
It's just
complicated. Yeah.
So you're saying that once you find one of
If you
these,
find one, then you have to argue why this doesn't happen generically.
Yeah.
And in fact, even having this lightest particle, okay, it supposedly saves us, but you might ask, why don't I take something like this? Let's take lightest particle and embed.
yeah, in the bigger.
No, this
where
guy.
kinematics looks like it's
Exactly that. This looks like a guy which has horrible solutions. But this lightest particle of maximal elasticity says once you embed it, it's fine. And even this, no one, I think, understood what's the mechanism. Like why is this?
Because you're saying, like in here there can be an
Exactly. There are acnodes.
But now the here is not n. I mean,
It's effectively two n's.
Yeah, exactly. So it's like if it were bigger.
Exactly.
So for some reason it actually works. This is why this thing has not been proven.
Yeah. And that's why maybe some people even, I don't know, that's something after you understand a little bit this kind of crazy stuff, then you ask why this doesn't happen. This no one has addressed. So people, use it, but even this diagram just explain the mechanism why this stuff does not propagate. It's quite unusual. So, yes, there is some basic physics mechanism to be understood. If this makes any sense, there is some mechanism that screens all this crazy singularities. Yeah.
And this is a thing. It's 4 dimensionals, or I mean,
This doesn't really care about dimensions. Any dimensions. Yeah.
But the idea is that it's hopeless to actually identify all these singularities
I think it's hopeless.
and integrate on them, right?
No, that's completely
So
out.
the only thing is to avoid them.
I think that's only hope. Either you avoid them and you're lucky, or even if you just take one loop box and try to understand it for general masses, it's horrible. Because you first have Mandelstam, but then Mandelstam presentation breaks down, so it's really.
I say it's not always. Is this like Charlie Lehman for 2D somehow? But it's a whole.
Yeah.
Nice. Can I even sit with this thing? You can take it off if you want, Sasha. You can.
Yeah.
I guess if it's 10 minutes, we can stop
it's
again.
already 10 minutes? Yeah.
Unless you want more.
No. Okay, let's continue then. So at this point, even though maybe in a very confusing manner, but I introduced you to the basic notions of S-matrix theory, and so now let's play some games where we can in fact apply them. And so the most I told you that the most famous result maybe is this Froissart-Martin bound, but the most famous tool, probably, or at least one very useful tool is what is known as dispersion relations. So we will now combine crossing, unitarity, analyticity, and let me remind you something which we discussed, which is a Froissart bound, and you can convince yourself that the Froissart bound can be also related to the following statement, that if you take an amplitude as a function of S and T, again I'm taking it for the scattering of identical particles, which are lightest particles, and you take absolute value of S to infinity, and you take here S squared, this is 0, as long as T less than 4m squared. So I can take it larger than S. So let's go to infinity, so I'll take T fixed and less than 4m squared. So what does it tell us? It tells us, again, this is a statement about the gap theories. This is a famous result. And it tells us that the amplitude cannot grow faster. In fact, it cannot even grow like S squared in the complex plane. Let's try to combine this fact with everything we already know. And one way to combine it, one simple way to combine it, is the following. Let me take the integral around infinity of the following function. Note that I chose three factors here, such that the denominator behaves as S prime cubed. The fact that this amplitude that grows slower than s squared means that at infinity, this guy behaves faster than 1 over s prime, say once s prime plus 1 plus epsilon. And this means that the integral over the contour, if I take a large contour in a complex plane, is 0. So this is the starting point. Now let me draw this in the complex S prime plane. There are, remember again, there are two cuts. And we can draw the following contour. So there is this part at infinity, and let me add to it this part. And there is another part at infinity. So this is infinity and this is 0. These are the cuts. So there is a contribution from the cuts. And now, because the function is analytic everywhere here, we can only pick the poles of this denominator, so it has poles. Let me put some S1, S2, and S. So therefore, we get the following identity. Well, the integral over infinity, which is 0, plus contribution from the cuts, is equal to contributions from the poles. So in here we see so far we just used analyticity and we use this bound on the rule of the amplitude. So this type of relations, this is what is known as dispersion relations, and let's work them out in some detail. Yeah, this is a really useful tool because, as you will see, we will find that we can use everything that we learned in some neat way to get some mileage out of that. So let me write the contribution from the poles. This is just plus well, the same contribution from the other two. It's in the notes, and you get plus a contribution from the cuts. So there is a 4n squared to infinity cut. We have Ts, and we have equally from minus infinity to minus t. We also have some Ts, which is defined as a discontinuity along these cuts, and here we have the denominator. Don't write. Now the next step we use is crossing. And crossing states that if you have a discontinuity in S, so what appeared here in this integral, minus t minus prime t is equal minus ts s prime t. So what happens here? Well, we're using crossing. I told you that on this cut, this describes the same physical process, and on that cut, the only difference is that this function from here is the same as a function from there. So that's why you get a minus, because here Ts means approaching an S-plane from above minus below. And unitarity here effectively keeps this minus sign. So after you use this and you combine all the terms, you get the following representation of an amplitude. So note that S1 and S2 are just constants. I just chose them at will. And you see that here we have these terms. This is just a polynomial in S. It's linear in S, and it depends on t. So we can write it as some f0 of t plus s of times f1 of t. So these terms, which are polynomial in S, are called subtraction terms. So we get them because we have to add these two factors to cancel this growth at infinity. So anyhow, this is subtraction terms. And then we have the last contribution, which is S1 minus S, S2 minus S. And here we have integral for m squared to infinity ds prime by ts s prime t. And here we have one, well, effectively it's just the same factor. So it's just the same product, which let me write it like I wrote it before. Minus prime. And here what happens, it's the same integral, I just changed s to u, and s to u, s2 to u1 to u2. Where the definition is u1 is 4m squared minus sy minus t. So the important point about this term is that you see that we express the amplitude as a polynomial times its discontinuity. And discontinuity, if you remember, when we were proving Froissart bound, it due to unitarity, it has positivity properties. More precisely, if you remember that Ts of S prime of t was given by the sum, imaginary part of Fj of S times Pj 1 plus 2t S prime minus 4m squared. And these Legendre polynomials are non-negative when, say, t is larger or equal than 0. And these guys are also non-negative because of unitarity. Okay, let's now we start with this, and we will use it as a tool to prove various things. So as a first, exercise, I will prove the following thing, which is called sometimes bound on scattering. So what is a bound on scattering? Bound on scattering is the following question. So we have discussed in the previous lectures what is the asymptotic, say what is the maximum asymptotic growth of the cross-section. We proved the frosts are bound. But you can ask, okay, well, we already discussed it. How do we know if we are asymptotically or not? We better want to prove some bounds locally. So we measure a cross-section at LHC. At some energies, we want to have some bound, which is a local bound. So let's try to prove, ask the following question. Is there a bound on the local growth of the amplitude? For example, could it have been that we measured the total cross-sections of protons at LHC, and instead of 0.08, we will find 2.08. The cross-section grows like that locally. Asymptotically, then it goes. That's the question we are asking, so that's why it's more useful. Now, okay, let's try to address this question. So to address this question, we take this equation, which is written here, and let me set in this equation S1 equals to S2 equal to 2m squared minus t over 2. The reason why is that it's because it's a crossing symmetric point. Because if you if you send it's to u, S1 to u, so if you evaluate 4m squared minus S1 minus t, you see you get back 2m squared minus t over 2. So it's just a nice point to have a crossing symmetric equation. And if you take this equation and evaluate it, you'll find that the right formula is this one. Now, one subtlety, if you might have caught me here, that when S1 is equals to 2, we started with this integral. Remember that at infinity it was 0, and now if S1 is equals to S2, we have this square. So when we take a residue, we'll have a derivative of the amplitude, and not just the amplitude itself, right? When we evaluate the residue of this pole, because there was this t s prime t here. So when we evaluate the residue of this pole, it's a derivative of the amplitude. I haven't written it here, and the reason is that it cancels by crossing. You can just show the derivative is 0.
So in the last one, you mean for m squared at the bottom, the very last thing.
This is u.
Sorry.
Yeah, the important point is that the amplitude is symmetric under crossing S to U. And this formula is manifestly symmetric. If you send S to U, this goes to itself. And you send S to U, this goes to itself. So this is a crossing symmetric formula. Now, something which already is nice is that this factor here, as I told you, if I take t to be positive, let's say between 0 and 4m squared. This is where we can write the dispersion relation, for example. So this thing is positive here. So we are getting a positive measure, and this positivity is a non-perturbative fact. It just follows from unitarity. It's not some perturbative statement. So whatever my full theory is, this guy is positive. So we might want to use it. So let's do it. And now I will do a few steps, and please watch my hands. Let me consider S, for simplicity, 2n squared minus t over 2 plus x plus iy. So I take S to be, let me to say, so this is real, because t is between 0 and 4m squared, and let me take x to be also positive and real, and y is also, I take positive and real. So I want to study my amplitude as a function of this complex S, where I just explicitly write its real part and its imaginary part. So, and moreover, let me take an imaginary part of the amplitude. So, if you do that, and let me now it's a function of x and y. And I just plug this formula into this formula. First, let me multiply by this prefactor and move this to the right-hand side. Yeah, first of all, this t at the crossing symmetric point, it has to be real. You just believe me. So it does not survive the imaginary part. And what is left is this formula. So this guy is real. So we are left with the following integral. Here we're evaluating this this TAS on the real axis, so it's effectively y is 0. Sorry, this guy depends on t. And these prefactors, if you plug things there, what you find is that you have 2 x, y, x prime, and here you have x prime square minus x plus iy squared times the same, which is complex conjugate. So you see that we find the expression for the imaginary part. And if I take x and y to be positive, you can see that every factor in this formula is non-negative. So this is non-negative, this is non-negative, this is just a complex conjugate product. So we get at this condition. Now, let me ask, I haven't defined what is the local growth of the amplitude, so let me do that. Well, and there are different ways to define it, but I will just define the way I want at the moment. And the way we want to define it is the following: we take dy y log of imaginary part of t of x and y and t. why is it a nice object? Why is it has anything to do with the growth? Well, imagine your amplitude behave locally. You measure it at the experiment. Let's say it behaves some s to the k. So effectively, this, if you evaluate it at x plus iy to the k, so then let's say y is small. So we just studying the behavior of this amplitude close to the real axis. So we have x to the k plus I y xk minus 1 dot dot. This is if y is small, and if y is much bigger than x, well, then we literally have that this guy behaves as just I to the k and y to the k plus ik minus 1 ik minus 1. And so let's say k is equal to 3, for example. Then you get here y cubed, and then when you take the log of y cubed and you differentiate dy y, you get k of 3. So that's why this is a reasonable thing to do. Effectively, if this object behaves as if this object behaves as y to some alpha, then log of y to some alpha dy dy will give us alpha. So this object measures the power of the behavior of this guy if locally it behaves like y to the alpha. Is that clear? Okay. So now let's compute this object using that formula. And with some hindsight, let me consider this object minus 1. And okay, it just happens to be the case that you find, if you compute this object, that it is equal to minus dx prime ts, which is non-negative. And here you get something which is the same denominator. It's here. And here you get x prime cs. X prime, the same denominator here. So in fact, you get that in every theory, this is always negative, where we used unitarity and we used some simple algebra.
Sorry,
Yeah.
didn't you set? So you set t greater than 0 to
T greater than 0 to argue for that.
So
Yeah.
this is not really the physical growth. So I mean, we're not in the physical region.
We are not in the physical region, but there is a generalization of this argument, I think, to the physical region, because you cannot just live with that, because Legendre's will not be negative, but if you average, you can.
Okay, and it's similar. So
But the idea I have in mind is also, first of all, T positive. It's controlled. So we discussed scattering in the impact parameter space in the first lecture with a signal model, and the picture of a signal model was an impact parameter space, which is exactly this region. So that's one comment. And the second comment is that, there is a more complicated generalization for negative t, tentatively. Now, what does it tell us? Well, it tells us that locally this object, this amplitude, cannot grow faster than linearly, right? Because it tells us that this object has to be less or equal than 1. So let me erase it. So there is some algebra, you can do it. And the important point here, every factor in this formula is sign definite. So we are good.
So I forgot, T of S is the amplitude divided by S. Is that what it was?
No. T of S is a discontinuity of an amplitude which is related to imaginary part SGFS, TK. And so because it's imaginary part, this is falling.
No, I was just wondering how it was related to the amplitude.
T of S is just imaginary part of the amplitude. Just the discontinuity of the amplitude across the S channel. It's not divided by S. So now let's take this bound and take some example. And remember, in our signal model, if we take something which looked like gravity, the bound was saturated. So let me take the T. Let's say we managed to measure, let's say, some impact parameter, the amplitude which grows like this. And this is how the amplitude grows with in gravity, for example. But here we can imagine quantum field theory, and we go to low energies, and the amplitude somehow locally behaves like that. So it's within maybe some EFT. So let's compute now the imaginary part of T S equal x plus iy. So we just get lambda xy. And if we plug it here, indeed this bound is saturated. So this amplitude saturates this bound, as it was with the signal model. Finally, you can also check that the fact that it has to be positive tell us that lambda. Yes, well, let me be more careful. So sorry. So let me take this, the imaginary part of this thing. So we get real part of lambda, xy, and we also can get imaginary part of lambda, and here we will get y squared. So this violates a bound, right? If I can take y, if I take y dy, and let's say y is larger than x, so this term dominates. So from here we conclude that from this bound, the imaginary part of lambda is 0. Now, from this term, we see that y saturates the bound, indeed, and lambda, the real part of lambda, if we plug it here, it has to be non-negative. So we conclude that, in fact, this power of this growth, of the local growth of the amplitude in this S-plane is maximal. So this number cannot be larger than 2. And if it's 2, this number is really positive. That's the conclusion. Yes, so that was, of course, maybe you would like to have a better bound of this type, which is that we don't take maybe this imaginary part, we just take the real part of the amplitude. But if you try it with the real part of the amplitude, so this sort of magic that everything works out positively, it doesn't work. So, at least to the best of my knowledge, this is.
When you say better bound, you mean more stringent?
Well, maybe you say, why do I have to take this complex thing and
But why do you call it better? Is it because it's not
other bounds? Maybe okay, other bounds. So okay, that was one example of something you can do with the dispersion relations. And this is something, again, just maybe to emphasize, this is not something you might easily derive from just based on your intuition, because, well, it is consistent with the signal model that we described, but in principle, the point you see that we can go in this complex S plane. S does not have to be small. So we can take, say, S to be quite large, but not too large. So we can take it at some intermediate energies, but not too large. So that's why it might be useful. Now let me discuss another application, which was very popular in the last year and still is a very active field. So let me erase it. And the topic is the following. It's dispersive bounds on effective field theories. So the idea is that
there is a question from Sergio. What would break if I gave lambda an imaginary part?
Sorry. Yeah, very good. So let me write you. So let's say T is lambda S squared, and this has an imaginary part. Then T behaves, if I take, say, Y larger than X, locally T behaves like this. And we derive the bound that this is less than 1. So if you plug now Y squared into this formula, you get on the left-hand side 2, and 2 is larger than 1. So that's the problem. Yes.
Wait, sorry. Can you repeat it louder somehow?
Yeah, sorry. The thing is, I see that it breaks the bound that we derived, but I don't see, because we didn't really specify what axioms we chose. I don't see exactly, if I were to use complex lambda, what it would break from the point of view of quantum field theory.
Well, it breaks unitarity effectively. I think eventually we will find that it breaks unitarity, and in fact, complex lambda is a kind of a boring situation because this T, it has to be it's satisfied as Hermitian analyticity, or so I think in a unitary theory, say if you write, well, how do you get this? How do you get this this amplitude? Well, just take your Lagrangian and add there T5 to the 4 times lambda. So if you make lambda complex, your Hamiltonian is not Hermitian anymore.
Yeah, thank you very much.
Sorry, but if I make a loop of this guy, then I get s to the 4 log with a log, right?
Yeah.
The log gives me I pi, no? And isn't that an imaginary part?
Yes.
S4 I pi.
Okay, let's do it. So you suggest lambda s squared plus lambda squared s to the 4 log s, right?
Yeah.
So
When you actually apply your formula, it doesn't.
you.
This is okay. Somehow.
Well, I think what happens is that if you want to violate, the bound, you'll have to take so y to be, say, larger than x, and what should happen is that just other terms we cannot neglect. Okay. But I mean, what I used is just unitarity and crossing, and so this has only 2 things, and the gap. So this theory is not gap. Let's say we don't care about that. Let's set t to 0, for example. N to 0. So in this particular case, yeah, making lambda complexes can be boring because it's clearly something you don't want to do. Okay, this was just one example, but let me now go to maybe a more interesting example, which is also something that we discuss in the first lecture, when I was motivating this approach. This is not a panacea. Of course, if you have, for example, a Drell-Yan process, so as Simone describes, you better use the QCD factorization formula to describe it. You don't want to start from the axioms, try to make a prediction for the LHC just because you will lose to QCD. It's much more useful for that purpose. However, if you are asked, okay, well, what about some extra particles? So if you go to higher energies, what happens? As long as you don't know, your theory, using the bootstrap axioms, it's an educated way to be agnostic. So we are simply relying on basic principles and we do not assume anything else. And therefore, this approach becomes useful and interesting when we imagine a situation where we don't actually know what happens and we want to constrain what are the possible scenarios. So that's why no one would use these bootstrap methods of dispersion relations, maybe to try to understand in detail things which you can compute with, with the QCD Lagrangian. But if we asked what would happen with the UV completion of the whatever standard model or gravity, this is the only way you can be agnostic and kind of proceed a little bit. So that's where it is. This method is hopefully useful. And this is precisely the settings that we will now discuss. So as I hope is clear, the dispersion relations already have in them unitarity, analyticity, crossing, everything we understand from general principles. And I think it's fair to say that in 2022, these are the principles. So we do not have any other better guess for the S-matrix. And so now the idea is, okay, let's try to apply these principles. And the idea is simply will be that. So remember that what is the rough form of the dispersion relation? It was that we have the amplitude, and it was given through the subtraction terms, maybe, the integral over the discontinuity. And so, and say, let me take the difference between the two, and it's equal to 0. And if you're effective field theorist, then you expect that you know your amplitude. We have a good control over our amplitude in some range of energies. So if we have some range of energies, somewhere here, we can call it IR. So if I choose S and T here, somewhere I can evaluate the amplitude, then I can maybe evaluate the contribution of the scuds just from our knowledge. So this is the IR. On the other hand, in the dispersion relation, this integral goes all the way to infinity. So it goes all the way to here. And here, we don't know what is the theory. We don't know what is the theory, so let me call it the So therefore, the way to think, the way you should think about dispersion relation in the context of effective field theory is the following equation: IR plus UV is equal to 0. And here, this IR is something we know, something, say, we can control at low energies, so, or it can be EFT. We can have our favorite effective field theory, be it Einstein theory, general relativity, or standard model, or whatever, fine Lagrangian, and the UV is something we might know or we don't know, but in general something we do not know. But we assume that it obeys everything we learned in the first lectures. So unitarity, we assume that this theory is quantum mechanical. Analyticity, we assume that it's causal in some maybe generalized sense, and we assume that it obeys crossing. And now the question is, given these principles and given your effective field theory, what is the interplay? What can you say about the UV starting from the IR? What can you say from the UV about the IR, or IR about the UV? And this is something maybe I'll just discuss next time, because this is a topic of some recent developments, and so maybe I'll spend some time talking about it.
Excellent. Okay. Urgent questions, just speak aloud. Otherwise, you can cook them for 5:30.
Feel okay, so I think I should be there. So far, feel okay.
So you'll survive to 5:30.
Should be fine. Yeah.
Last famous words found in bed 2 days after. Okay, so we can finish the lecture, and thank you all for participating.